sort where we were. So yeah, we discussed perturbative quantum gravity in the last lecture, and now I want to present the other possibility, except for the third possibility to like completely modify our theory. The second possibility to basically gravitize the quantum interaction, right, or to turn the quantum part in Einstein's equations into something classical. And the easiest way to do that, so if we have Einstein's equations with an energy momentum tensor for quantum matter, sorry, but then the easiest way to get something classical on the right-hand side is to simply take the expectation value of this energy momentum tensor in some quantum state, right? I mean, in the most general case, you would need to include the wave function of all particles in the universe, or you consider some subsystem and yeah, just the wave function of that. These equations, are called the semi-classical Einstein equations. And they are actually relatively commonly used, but it's important to point out that they are usually introduced in a completely different context, namely as the mean field limit of some quantized theory of gravity, right? So if you have some quantum theory and you're considering the case where you have a lot of particles, basically, then in the same way you can do like Hartree approximations in quantum systems of many particles. You can get the mean field limit of this quantized theory, and you will get the same type of equation, but with a completely different meaning. So there it's really an equation that emerges as an equation for like a condensate or a collection of possibilities. And in this context that I want to discuss it now, it's assumed that this is actually a fundamental equation in a sense, so that fundamentally space-time is classical, and we have quantum matter living on this space-time. So now, fundamental is a big word, right? What I actually mean when I say fundamental is I present this as an alternative to this perturbative approach that I discussed in the previous section. So. So you could think of that. I forgot the headline. Semi-classical gravity. So the way I like to see it is, so you could think of some underlying theory that we don't know yet, and whatever this theory is, this full theory, let's call it quantum gravity. It will somehow have a limit that gives us quantum theory the way we know it. In the most general case, quantum field theory on curved spacetime. So that must somehow be a limit of this theory. On the other hand, we also want to have general relativity, classical general relativity, as some limit of this theory. And so the question is basically, whatever this unknown theory of quantum gravity is. In this case where we have quantum matter basically that we cannot approximate by a classical space-time, and where we can't treat gravity just as a background, but need to take this back reaction into account. What is the right approach to do that, right? Is it a good approximation to use this perturbative quantum gravity that I presented previously, or is it maybe a good approximation to use this approach, to use the semi-classical Einstein equations, or it might also be that both of them are not very good approximations, any reasonable limit. So if we have this just as an assumption, as a hypothesis, how nature might work in some regime at least, then one might first ask, okay, is this a consistent equation? Can we actually do something with this? Is this in contradiction to any principles? And there are actually such arguments. And the probably most cited one is an argument by Page and Geiger, who propose an experiment which they claim shows that this equation is wrong or cannot be correct, quantum mechanical. And the experiment goes as follows. So what we have is a torsion balance, right? So we have some test masses that can be basically in one of two positions, A or B. And we have some pointer, right? In the simplest case, that's usually some laser ray or something. But so what happens is that if our masses are in position A, then we will get our pointer will be so our test masses here will be attracted by those masses, just the usual Cavendish experiment, right? So you will get some mark somewhere here at the end. So you will see a gravitational effect that shifts this pointer to while when you're in position B, of course the opposite happens, and you get a point here. Now, that's a purely classical experiment. There is nothing interesting happening here so far, except that you can measure gravitational constant if you do it precisely enough. But what they did now is they used a quantum system as a decision-making device. So they had some cesium particle that was decaying, and then they had a counter. They had something like, this is kind of an idealized version of this experiment, but so essentially they have, let's say, okay, you have one counter, and you measure over a certain time, right? So you have a certain time over which you measure, and with 50% probability, you get a click, and with the 50% probability, nothing happens at your counter. And now there is the experimenter registering if there has been a click or not, walking over to this torsion balance, and if there has been a click, then he puts the torsion balance in position A, and if there has not been a click, then he puts the torsion balance in position B. And surprisingly, the outcome of the experiment is when the torsion balance has been put in position A, then the pointer points on position A. When the torsion balance has been put in position B, then the pointer points in position B. So what does that tell us about semi-classical gravity? And there, the argument that they do is basically the following. If you have your state of your cesium here, right? And you have some state of your torsion balance, I don't know, let's call it chi, then this experimenter doing this experiment and setting the torsion balance entangles those two states. And what you will actually have here, if you have a superposition here, so you have a superposition of click and no click, right, will become an entangled state of there has been a click, and the setting of the torsion balance is A, with there has been no click, and the setting is B. And now if you take semi-classical gravity and calculate the gravitational field of such a superposition state, then the gravitational field of this state will be the field where half the mass is here and half the mass is here. So in this state, the pointer will actually point to this position C. So what is wrong with this argument is, or well, what does this argument show? Let's put it like that. Well, so this argument shows that in an that in a formulation of quantum theory where you don't have a collapse, semi-classical gravity cannot be right. If you don't have a collapse, then this is the correct formulation, and yes, and you don't see the pointer. You don't ever see a pointer pointing on the middle. It will always either point on B or on A. However, this is not a valid argument in any other interpretation of quantum mechanics, where you have a collapse here already somewhere at the latest when the person actually reads off the state. You will have either this state, or you will have this state. And here you will get either this part or this part and no superposition of the two. So there is a second type of argument that is a bit more general by Epley and Hanna. And so the basis there is just assume you would have, so basically they try to exclude any semi-classical coupling of any type of semi-classical coupling of gravity to the other interactions. And their argument goes roughly as follows. So assume you would have classical gravity, right? Then you have classical gravitational waves. And since classical waves don't have to obey the de Broglie relation, that the momentum is always the inverse proportional to the wavelength. So this is not to be true for a classical wave. You can have arbitrarily short wavelengths while still having small momentum. So you can, in principle, if you have a quantum particle, you can, by scattering a gravitational wave at this particle and making the momentum of this gravitational wave very small and also making the wavelength very small, you can, in principle, determine the position of this particle without disturbing its momentum, and thereby violate the uncertainty relations. So, so they basically, what they do is so they discuss two cases. So this would be the first case. So the first case is that the gravitational wave causes a collapse of the wave function, right? So in this case, you get exactly that. So you get a violation of the uncertainty principle, or momentum conservation is violated. And to this, you can actually argue that while this is true, that at the regime where this is relevant, right? The uncertainty relations are not something that has been experimentally tested. So there is no fundamental reason why we should believe that the quantum uncertainty relations also in a modified theory of quantum in a modified quantum theory should still remain true at all levels. The second argument against this is that even if you have a semi-classical coupling, you can actually show that such a system where some classical system is coupled to a quantum system, there is always a certain transmission of uncertainty from the quantum system to the classical system. So this condition that for the classical wave, momentum and wavelength can be chosen arbitrarily small, might actually not be correct. The second case, and that's the one that will be more relevant for what I want to discuss, is the one where no collapse of the wave function happens. So where this scattering of the gravitational wave is actually a scattering at the wave function and leaves the wave function intact. And then the argument is you have basically this way you have access to the shape of the wave function. You're scattering at the wave function, so you learn something about the wave function itself without having to collapse it. So this way you can have faster than light signaling. I will discuss that with the Schrödinger-Newton equation in detail later. But there is actually in the paper another paper by Mattingly. So he actually analyzes the thought experiment that they suggest in more detail, and says that at least for the experiment that they propose in order to get this violation, that this experiment is not possible in practice. So the way they suggest the thought experiment, you would need a detector that is so massive that it would be inside its own Schwarzschild horizon. So then what Mattingly says is that, well, while of course a thought experiment is nothing that you have to be able to do in a lab, it must still be possible to do it in principle at least. And if you need to have a detector that's sitting inside a black hole, then you can't do this experiment even in principle. So while those are arguments that are certainly to be taken seriously, and that suggests to be very careful about how seriously you take this equation. None of those is really a conclusive evidence that this equation must be wrong or does violate known physics. Okay, now that we have that, I would like to talk, just as we did before for the perturbative quantum gravity. I would talk also in this case about the Newtonian limit of this theory. And since we already learned about the Newtonian limit in GR, this works essentially the same here, so I don't have to say much about this. We have the Einstein equations, the linearized Einstein equations. Yes, of course. Yes, yes. Yes. No, because I don't really know much about that. But we can discuss that later. I would be very interested to discuss that. Yeah. So. So we had the Einstein equations. And now we just replace T mu nu by the expectation value. And just the same way we did that for the classical theory, we can get the Poisson equation from this. So we get Laplacian of the gravitational potential is 4 pi g. And then we have the expectation value of rho operator. And now we do the same thing that we did for the quantized theory, right? Where we where we had also found that the coupling is with T00H00 if we took that Fierz-Pauli Lagrangian, for example. But the difference now is, so in the quantized theory, we had a hat on both of them, right? So both our metric field and the stress energy tensor were quantum operators. And now we only have a quantized matter, but a classical spacetime. So this is actually proportional to rho operator, but a classical gravitational potential. So, and then you can just integrate this Poisson equation. So we get minus g integral E3r prime, expectation value rho of r prime divided by r minus r prime. And we can get the interaction Hamiltonian the same way as before. So in second quantized form, we have then minus g integral d3r and d3r prime. And now we have a rho operator at r. Times the expectation value of rho at r prime divided by r minus r prime. And this is, again, if we use that the mass density operator is just m phi dagger phi. We get minus gm squared integral, and then we have phi dagger and r, phi and r, but then we have the expectation value of phi dagger r prime, phi r prime. Okay, now if we evaluate that again for an n-particle state, then what we get is that the excuse me. Actually, if I evaluate that for a one-particle state, so with a one-particle state, that is r psi of r. Sorry. So if I evaluate that for this state, then the expectation value here is just absolute value psi squared, and we end up with the one-particle Schrödinger-Newton equation that we already saw before. So I h bar psi dot equals, and then we have minus h bar squared divided by 2m, the plus operator, minus gm squared integral psi of t r prime, absolute value squared, divided by r minus r prime. Okay. So you see that we basically did the same thing in both cases for the semi-classical theory and before for the perturbative quantum theory, and we end up with two very different types of interaction in the case of the Schrödinger equation. And this equation is, however, a nonlinear Schrödinger equation, right? So you see that that the potential here actually depends on the wave function, which renders this equation nonlinear. And the problem of such nonlinear equations is that in general they allow for superluminal signaling. And in the Schrödinger-Newton case, this is relatively easy to understand. You can just think of the following experiment. You create a superposition state somewhere. Of so you have an experiment. So basically, what you do is you have at a position. So you have two entangled particles A and B, and you have a Stern-Gerlach device at one position, right? And like very far apart, you can have another Stern-Gerlach device. And so you create this entangled, this pair of entangled particles, A and B. So they will be in the following superposition state. So if A is spin up, then B is spin down, and the other way around. And now you bring particle B to the one device and particle A to the other device. And now you can agree on some measurement protocol. And in the easiest case, you have like one experiment on Earth and the other one on Alpha Centauri, and then you just agree with your colleague that, well, tomorrow at noon intergalactic time, we both sit in front of our measurement devices, and if I want to signal you a 1, then I do make a measurement of the state, and if I want to signal you a 0, then I don't make a measurement. So what happens here? Well, we have the superposition state being split up in the two possible states that correspond to spin up and spin down. So if my colleague at A does make a measurement, then this wave function will collapse, right? So I will have either this case, and then find a dot on my screen here, or I will have this case, find a dot on my screen here. But in the second situation, when at A there is no measurement, then the superposition remains in a superposition. And now what the Schrödinger-Newton equation tells us is that these different parts of the superposition, they are just parts of the same wave function. So since actually the wave function determines the gravitational potential, the state here will feel the gravitational potential of the other part of the superposition. It will be attracted towards the middle. And the same is true for this one. So in fact, the two will move towards each other. And when they finally are measured, we'll give you a dot somewhere in the middle. So basically, by doing this measurement, I can tell if at A there was a measurement. So if I get a signal, 1, or if there was no measurement, so I get the signal 0. So this is clearly a problem. The thing you have to take into account here, or the thing that you have to still be careful about, is that in order to do this prescription, we still use the regular Copenhagen measurement interpretation, right? We just assume that as soon as a measurement is made at one place, the wave function at the other side collapses. But this outcome actually remains true in any of the theories for collapse that we currently have available. So it doesn't matter if you use collapse models, or if you think of it in terms of well, many worlds is incompatible anyways. We learned that already. So yes. Yes, it is. Exactly. It's a gravitational self-interaction. Well, why wouldn't you? I mean, other than this argument. Well, you know, in classical electrodynamics, you have that too, right? You also have particles feeling their own fields. And I mean, in some sense, you also talk about self-interactions in quantum field theory. Although there it's more like, sorry. What? Yes. Yeah, exactly. I mean, the point is that you have the wave function, right? You think of course, you have to get rid of this interpretation as the wave function just giving you like some probabilities and not being something real. In this thing, you really have a concept of wave function that is somehow yeah, something real. So the wave function is really what corresponds to the mass density that generates your gravitational field. And in this sense, there is no problem with the theory. But this faster than light issue is something that is to be taken seriously. And I don't know a way around it. The only thing that I know is that in principle, there could be a loophole with like having to choose a completely different collapse interpretation that nobody thought about before, right? So the reason why this equation still is very interesting is because we can experimentally test it. And to, how much time do I still have? Okay. To explain, so first of all, if you look at this one particle equation, what does it actually predict? If you just have a Gaussian wave packet, then in standard quantum mechanics, what that will do is you have the free evolution of the Schrödinger equation, so your wave packet will spread over time, wider. And if you now take the self-interaction into account, then this evolution is not really a free evolution anymore, but every part of the wave function feels the gravitational field that is created by the rest of the wave function. So what happens is actually that if you have enough mass in your wave function, then at some point the gravitational attraction of this wave function becomes large enough to compensate this spreading of the wave function. So what you will see first, if you increase the mass, is that instead of the quantum mechanical behavior, you will have some slightly slower spreading. But then if you increase the mass even further, eventually you will have a situation where your wave function actually starts to shrink inside. And the way that happens is there are stationary solutions of this Schrödinger equation. They aren't Gaussians, but they look kind of similar. So what happens in principle is that there is somewhere there is this stationary solution. And what the wave function does then is that it tends towards the stationary solution, and then it starts oscillating around that and approximates this stationary solution and tends to go into this stationary solution. So that's just a soliton like you also have in nonlinear Schrödinger equations in nonlinear optics, for example. So that was the first suggestion how to test this equation in an experiment. Was you can do interferometry or just basically what you have to study is just the free spreading of the wave function, right? But if you do an interferometry experiment, then you expect that at some point your wave function basically doesn't reach both slits anymore, and your interference pattern will get lost. So that happens for masses around. So if you use the experimental setups that currently exist, then that happens for masses of about 10 to the 10 atomic mass units. And current experiments have like 10 to the 4. So that's still a bit off, right? But it's much closer than what, for example, you have as numbers when you want to test Planck scale effect in quantum gravity. And then what you can actually do is you can you can look at the Schrödinger-Newton equation for many particles, and you can just, in the same way, from the same derivation, you can get a many particle equation, which I won't write down now, but the point is, this is on the page, oh no, here. Or I can also write it down. So if you have n particles, then the gravitational potential in the Schrödinger-Newton equation will actually be sum over I and J, G, I and J. So those are the masses of our particles. And you get an integral with the n particle wave function squared, and then you have Ri minus Rj prime. So in this equation, you have both the mutual interactions of different particles. So if I and J are different, then that's just the standard interaction of two particles, the Newtonian gravitational interaction. But you also have the terms where I and J are equal, and those are exactly the self-gravitational interaction where a particle feels its own gravitational field that's generated by its wave function. And now you can separate this equation into center of mass and relative coordinates. Since it's a nonlinear equation, it doesn't separate exactly, but you can do something like a Born-Oppenheimer approximation, where you take into account that all the internal interactions, all the electromagnetic interactions that keep your particle together are much stronger than the gravitational interactions. So these interactions have a much faster time scale with which they are happening. And then just with the usual approach that you do the Born-Oppenheimer approximation, you get that the gravitational potential that enters in the center of mass wave function has the following structure. It's minus G, and then you integrate, or basically you have a convolution of the wave function, or the modulus of the wave function, with a function that I call I rho. And I rho has the following form. It's integral d3x, d3y, x of y minus d divided by x minus y. So this I rho is just the gravitational self-energy of a mass density rho with a copy of the same mass density shifted by this distance d. So that's how I can imagine this function. And you see that when I take the limit of a point particle, so if my rho is a delta function, that you get back exactly this one particle equation. What you can do now is this I rho can actually be calculated. So if you have a spherical distribution, for example, for a sphere, this gravitational self-energy just takes the form, it's m squared divided by r times, and then you have 6/5 minus 2 eta square, I will define that in a second, plus 3/2 eta third, minus 1/5 eta. This is for eta smaller than 1, where eta is just d divided by 2r. Question? Okay. And it's r divided by d for eta larger than 1. Or you can do the same for a Gaussian mass distribution, and you find that this rho in this case is just m squared divided by d, and then the Gauss error function d divided by square root 2 sigma, where sigma is the width of your Gaussian wave packet. So with this, you can in principle calculate this gravitational potential for different mass distributions, and sorry. Okay. And you get a behavior. You can. I need some space somewhere. So if you have the case where you have a wide wave function, so let's say okay, so your wave function is much larger than the radius r of your mass distribution. So you have a spherical particle which has a wave function that is much wider. Then you just get the one particle Schrödinger-Newton equation, and you get exactly this behavior that I told you before. So you have the slower spreading in the excuse me, in the case in the opposite case where you have a very narrow wave function, what you can do is you can expand your potential and for small values of d. So so what you get here is minus g I rho at 0, and then you get at second order you get minus g half the second derivative of I rho at 0 times an integral of psi squared r minus r prime squared. So which is just r squared minus 2r times the expectation value of r plus the expectation value of r squared. And this equation actually, so this here you can write as an m omega squared half. Right? So you basically get a harmonic oscillator where this frequency omega. Oh, I have to. Excuse me, I'm too fast. Okay, so this omega squared omega squared is g divided by m. And the second derivative of I at 0. So if you take the spherical, if you take the spherical particle, then you get m squared divided by r to the third. So this is just plus. I forgot a minus somewhere. No, the minus is already on. Okay, so this will be just g rho. So omega is just square root of g rho, depends only on the mass density of your particle in this narrow case. And the best you can actually do with the materials we have on Earth is osmium, which has the largest density of all elements, for which you find that this frequency omega is of the order of 1 millihertz. And this you have to compare now with what you have in quantum experiments, right? When you have a harmonic oscillator or you have a particle trapped in a harmonic potential, then you basically get a correction of this size to your frequency in the harmonic oscillator. There is one thing that I just very briefly mentioned now. So what we didn't consider here is that when you have matter that has actually a crystal structure, then if your wave function is wide, then you can ignore this crystal structure completely, and you can treat it as if it was a homogeneous sphere. But if you have a wave function that's very small, so that it actually can probe this structure, then you can't model this by a homogeneous sphere anymore. And if you do that correctly and take this structure into account, then you see that that improves these values significantly. So you actually get in this case an omega that is proportional to square root g times the atom mass divided by sigma to the third power, where sigma is basically the localization of your atoms inside your crystal. And then you can do that also for different materials. And if you do that, for example, also for osmium, then in this case, you get something that's more like 300 millihertz order of magnitude. So yes, so you can improve this a lot by actually taking into account that you have a structure in your crystal. Yes, and we actually proposed an experiment, so you can do two types of experiment there. In principle, the one thing is if you have a squeezed state in a harmonic oscillator, right? Then this state will oscillate internally, so the wave function will oscillate, while at the same time your whole particle oscillates. And in the standard theory, those two oscillations are completely in phase. They happen with the same frequency. And this Schrödinger-Newton effect only changes the internal oscillation, so you can actually see that the two oscillations will not be in phase anymore. So this is one observable effect, and the other effect that we with Hendrik proposed as an experimental test is that when you now go away from this narrow wave function limit and you make your wave function wide enough that it becomes of the size of your particle, or in that case of the size of the atoms, then this omega becomes a function of the wave function shape. So you have a frequency that depends on the shape of your wave function. So other than in the standard harmonic oscillator, where all the energy eigenstates are just separated by the same distance, you will actually get a separation that depends on the shape of the wave functions. So you will get a deviation of the spectrum of an harmonic oscillator. Exactly, and it turns out, and I think Hendrik will talk about that. Okay, so Hendrik will talk about that. No, I don't say anything. No, it turns out that this is actually an experiment that is, at least in principle, seems feasible with current technology. Okay, then we still have 30 minutes. I wanted to talk about my notes. Yes. Okay. So 5.4, I think. I want to talk about gravity and wave function collapse. There are arguments that gravity might actually the reason why the wave function in quantum mechanics collapses, and so one of the probably most famous proponents of that is Penrose, who suggests basically explains the following situation. So in quantum mechanics, if you have two stationary states, alpha and beta, that both have the same energy, so you have IH bar dt of alpha equals E alpha, and you have the same time evolution for your state beta. And now you think of that you can take a superposition of these states. So you have some superposition psi, which is A times alpha plus E times beta. Then according to the rules of quantum mechanics, linear superpositions, this is also a stationary state with the same energy E, so you can just calculate that. You have IH bar dt of psi equals, well, this is A times the time evolution of alpha, which is E alpha, plus B times the time evolution of beta. So we have E times psi. In this sense, you would have a massive particle, right? That is in a superposition of being here and being here. There is no reason why it shouldn't be. That is either here or either here when we observe it. There is no reason why it shouldn't be in a superposition state of those two, since they are just as well described as stationary states by quantum mechanics. So there is no reason why a system in this state should go into one of those two states, why we shouldn't observe it in this state. Then Penrose points out that we actually have to be careful about what this what does dt actually means in our equation when we talk about gravity. So if we have only the state A or alpha or only the state beta, then we have a approximately classical space-time. We can say in good approximation, we either have the state where the particle is here with some space-time that is curved here. That's the one situation. Or we have the particle sitting here with another situation. But in both cases, our space-time can be approximated by a classical space-time, and the dt is then just or approximately is the killing vector that belongs to or that represents the time displacements of these stationary states. But the problem is that those two dt's in those two situations, they are actually different from each other because they belong to different space-times. So we cannot identify one with the other, and our quantum mechanical description requires some dt operator that also applies to the superposition. So we need to know what this dt is that acts on the superposition, and we can't somehow write it build up of those two because they are living in two different space-times that we cannot compare. And now what Penrose says is what can actually be done is we can approximately identify those two. Right? So we can approximately say those two dt's are call them alpha, beta, right? So they are approximately equal. But when we do that, we make an error, and this error that we make is exactly the gravitational self-energy of the superposition state that we would have if we both have both of them in superposition, which so you can then use Heisenberg's uncertainty principle for the energy. So from the time energy uncertainty, you can derive a lifetime of this state that is this gravitational self-energy divided by h bar. And so according to Penrose, then within this time scale, this superposition state would actually reduce to one of the two possibilities. Similar ideas have also been written down already before Penrose did that, and so most famously by Dioschi. But I want to discuss another model here, which is the one of Karoli Hasi. I must admit I have no idea how to pronounce his name. I'm apologizing when I pronounce it wrong. So the idea there is basically that that when you have let's say you have a wave packet. If you think of this moving through space-time, then it will create some word line segment in space-time, and now what you do is you use the uncertainty principle. So delta p times delta x equals h bar divided by 2. And from this you get a velocity uncertainty, which is delta p divided by m, so h bar divided by 2m delta x0, where x0, or where this delta x0 is the initial wave function spread. And and the final spread of the wave function is delta x, which is obtained by delta v times the time that the particle or the wave function propagates. Right? So this is actually d times t. That's the length of this word line element, and now we try to minimize the uncertainty of this word line segment, and this is achieved if these two delta x and delta x0 are actually equal, which then implies with those two relations that delta x squared equals h bar t divided by 2m. Okay, and this we call delta s squared. That's the uncertainty of this word line segment. We have the length s of the segment is c times t. So so we get t here, and get delta s squared equals h bar s divided by 2mc. And now what he assumes is that this uncertainty should not be smaller than the Schwarzschild radius of this particle. So the wave function must at least be spread wide enough that that it does not lie within a black hole or within the Schwarzschild radius of the particle itself. So that's the condition that delta s is smaller than gm divided by 2c squared. And now you can, so from this we compute that the mass is smaller or equal 2c squared delta s divided by g. What? Sorry. Why not gm divided by 2c squared is the Schwarzschild radius of the particle? Oh, sorry. Yeah, I think then the rest of my calculations also not. Like this. So okay, so the point is it doesn't really change much about the argument, but thank you for pointing it out. So I just have to find again where it was. Okay, so we get that delta s squared is larger or equal. We have h bar s divided by 2c, and now we have 2g. Yeah, that also makes more sense. 2g divided by c squared delta s, which results in delta s equals or larger or equal, so that we get a minimal delta s of h bar gs divided by c to the first. Power 1/3. So And the idea is now to replace the metric G mu nu by an ensemble or a family of metrics G mu nu that are labeled by some index J. And that are distributed around this G mu nu. So they are all close to this G mu nu, but have a certain variation. And the uncertainty of this variation of the metric is chosen such that it actually matches this delta S uncertainty. So we demand that delta S squared, so delta S squared is then defined as the usual variation. So the S in the metric Gj minus the expectation value of the matrix squared expectation value. So this quantity we actually require to be equal to this number that we calculated. And yes, and then we find then we find this. So yes, so we find yeah, okay, sorry. Yeah, so we demand that those two are the same, and now you can show. So what follows from that is that has been shown by Franke that there is you can introduce a coherence length that follows from that, which is h bar squared divided by g m to the third. And the behavior of a wave function is now basically such that as long as it is outside of this coherent, as long as it is inside this coherence length, it will just evolve like in Schrödinger dynamics, right? But if it gets out of this coherence length, then those different metrics in this ensemble will yield different phases that add together in such a way that they actually decohere the wave function and lead to the collapse. And the values of this are such that for a proton, one gets something of the order of 10 to the 23 meters. And if we take something with like the usual mass density and 1 centimeter radius particle and mass densities of like 1 gram per cubic centimeter, like we find it on Earth, then for such a macroscopic particle, you get a coherence length of 10 to the minus 18 meters. So this actually reproduces exactly the behavior that we expect, that for a system that is clearly a quantum system, we have a really large coherence length, so we never expect it to collapse, while for a system that we would consider as macroscopic, this coherence length is so small that it will practically always be collapsed. Okay. So I still have a little bit of time. Just as a short remark, so this length scale actually also appears in the Schrödinger-Newton equation, where it is the order of magnitude of the size of the stationary states. So that's quite interesting that there are some similar length scales of the two equations, and that this can be shown relatively easy. If you look at the Gaussian and just the solution for a free Schrödinger equation, then the evolution of a Gaussian state is as follows. So we have the normalization factor, and which is also time dependent, IH power T divided by M sigma squared minus 3/2, and exponential minus R squared divided by 2 sigma squared 1 plus IH bar T divided by M sigma squared. And now you can do the following. You can first of all you can take the radial probability density, which is 4 pi r squared expectation value psi squared. So for a spherically symmetric wave function. That gives you basically the probability that you find in a shell at radius r, and then you can calculate the peak of this probability, which you find at sigma times square root 1 plus h bar squared t squared divided by m squared sigma to the 4th. And now you can take the second time derivative of this at time 0. So and you find that this is h bar squared divided by m squared a to the 3rd. And now you can just compare this to Newton's law. So you demand that this acceleration of this peak shell kind of should just follow Newtonian acceleration. So this acceleration should be gm divided by the distance squared, which is a. And then if you do this, then you will get that a has exactly the same value. It's also h bar squared divided by gm to the 3rd. So yes. So in this sense, there seems to be there is some connection between this approach and the Schrödinger-Newton approach. Nevertheless, it's important to point out that Schrödinger itself is not a collapse equation. So the Schrödinger-Newton equation does not explain the collapse. It still needs some collapse prescription, mainly because you can't recover the Born rule if you have a superposition in the Schrödinger-Newton equation of a particle being here and a particle being here, then the self-gravitation will just basically move the two parts together, and you will finally observe the particle in the middle, while of course in collapse you expect it to show up like here with half probability and here with half probability. So in this sense, the Schrödinger-Newton equation is just as incomplete as standard quantum mechanics. Oh yes, yes, yes. Yes, yes, yes. Yeah, I think actually, yes, I think that if you're searching for the solution to the collapse problem in gravity, then I mean if you want to explain the collapse by some other interaction, then it's clear that it should be some non-quantum interaction, right? So so in that sense, if you want to use gravity, then you basically have to require that gravity is not quantum. And then I think it makes sense to actually take Schrödinger-Newton seriously. So whatever your collapse mechanism is probably something that needs to be taken together with something like Schrödinger. So in that sense, yeah. Yes, exactly. Well, I mean, the problem is the stochasticity, right? There is just in GR there is not so much room to introduce. I mean, you have to put it in by hand somehow. Just yeah. Yes. Oh, because they are just two different realizations of they are. So when it's a superposition, then you can of course require that you have one spacetime, and that's kind of what, well, yeah, what Penrose kind of does, right? He assumes that there is still a classical spacetime that belongs to that to this state somehow, or well, it's not really clear actually. But if you have either the state alpha or the state beta, that's two independent situations. You just say, okay, I have the one with one spacetime, or I can have the other with another spacetime. No, but they are two solutions of the Schrödinger equation. They are two solutions of your quantum dynamics, and linear quantum dynamics tells us that if we have two solutions, two stationary solutions with the same energy eigenvalue, then their superposition is also a solution. And the question is, if this solution exists and this solution is just as real as alpha and beta as solutions in quantum mechanics, then yeah, why don't we see this solution? I mean, yeah. Okay. Let me just see. Yeah, I think I will just end at this point. I had a chapter 6 planned, but I didn't really do so much for that anyway. So I think this is a good point to stop. And yes, I'm happy to still discuss for the last couple of minutes. Yeah. Yes. I'm not sure what it's from all the elements we know. It's the largest density. Yeah, I mean it's. Yeah. That's what. Yeah. I don't. I don't think it matters. I mean, actually, also the mass density doesn't matter so much. It's because you see, it's only if you have the mass density dependence, then it's only a square root rho dependence, and the mass densities of the different elements that we have on Earth aren't actually that different from each other. They differ by like 1 order of magnitude, as long as you don't want to do it with a gas. So you don't really have a large effect from the mass density, anyways. That the important point is that it's yeah, but like 1 order of magnitude, you can basically vary it. Yes, exactly. The important point is that it's not a mass-dependent effect anymore in this narrow regime. So once you made your particle so big that your wave function basically is smaller than your particle itself, all that matters is the mass density, and you can continue to increase the mass, and you're just not getting any better. That's basically the message. At some point, it just doesn't help anymore to make the mass bigger. You have to get your wave function wider too. Yes. Yes, page, I can, I just can't do it. Yes. Yeah, I can actually, yeah, okay. So the two experiments actually that I mentioned. Yeah, you can also, if you look at the paper by Mattingly that I had in the list, yeah, when I gave you the list this morning, there was the paper of Mattingly, is quantum gravity necessary? There, the two papers are definitely cited as a reference. So if you just look in the references, there you will also find it. Yes. If alpha and beta can have the same space-time. Yeah, of course, you could have two states that only are internally different. That's probably also not exactly true. If you have two different spins, you also will have different gravitational fields because spin also sources the gravitational field. But of course, you can have approximately a similar space-time. I mean, you could. You're trying to think of a situation where you can have superpositions that, according to this, would not collapse. Or yeah. I'm not sure. Yeah, exactly. So the point here is to have the same mass basically at two different locations, which are the two states that you're describing, right? But you are, of course, right that in principle I have to also explain why a spin state can collapse, right? Although then you have to consider also the entanglement with massive systems, right? I mean, that's in general, that's, yes, exactly. In general, the description is that you have some pointer that is a massive system, or yeah, it's a macroscopic system, and then because you have them entangled, if this pointer gets displaced, basically, then this also collapses. Yes, exactly. Because gravity is the only force of the four that we know, which we don't know if we have to quantize it, right? I mean, for the other three, we kind of know from experiment. For this type of argument, well, I wouldn't know how you would do such an argument in a quantum theory. That's just the problem then, that you have a linear theory and you just don't. Yes. Also not. Yeah. Yeah. Okay, that's true. Yeah. But yeah. But I think the main difference is still the nonlinearity that you can have, right? I mean, um, okay. Yeah. Yeah. That's okay. That's probably true. Okay. Okay, then if there are no further questions, I guess we can also still discuss. I'm still here the whole next 2